Good morning. I wanted to go over the log laws and the laws of exponents because I didn't go over them in class and I wanted you to have one clean place to look at them. So right now I'm just going to ask you to spit out the log laws and laws of exponents on tomorrow's quiz. However, in the future quizzes, I'm going to ask you for examples of where it's being used. So what are the laws of exponents? The first one is that x to the n times x to the m is x to the n plus m. So how do we apply this? Well, in this case, my n is 1/2, my m is -3. When I take x to the n times x to the m, I would add the exponents together. Now notice I've taken more complicated looking exponents. I did this on purpose because everybody seems to know when n is 2 and m is 3 what to do. But when we have more complicated numbers there, it starts to look a little messy and you really have to know the rule. So we have here, I got a common denominator and I added 1/2 to -3 and I get -5/2 as my result. So here's just a reiteration that in this case, in this example, where I run through this x to the n times x to the m, n is 1/2 and m is -3. Second one is when I divide, I have x to the n divided by x to the m, it's x to the n minus m. So here's the same example, but now I have division. In this case, n is 1/2 and m is still -3, except now I subtract the exponents. So I get 1/2 minus the -3 in this case, which is 1/2 plus 3, and getting a common denominator, I arrive at x to the 7/2. So again, here in this case, I'm applying the second rule with n equals 1/2 and m equals -3. But many people skip are not careful with this when it's part of a longer calculation and then get it all messed up. So I would advise actually saying what my n and m are at the beginning when you're first starting these problems to ensure you don't make a mistake. Here's another one. A to the p, b to the q in parentheses raised to the n. Well, in this case, every single one of the exponents gets a little n. And you see the n is drawn in, we multiply the exponents. So if I had, in fact, in this case, a equals x, p equals 2, y equals 1/2, and we have n is -4, we just multiply the exponents together and arrive at x to the -8, y to the -2. This is pretty easy to implement. Most people make a mistake when there's something in the front of the x squared and y to the 1/2. For example, if there's a 3 there. But you have to keep in mind that everything has a power. If it doesn't have the power expressed, it's really to 1 power. And so in this case, we would multiply also the exponent of the 3, which is 1, by the -4. And that's most often forgotten, but not by you guys. You guys will remember this because I pointed it out to you. Negative exponents can drive people crazy. All it means is that it is the positive exponent kicked to the denominator or numerator. So for example, if I have x to the -m, that's really 1 over x to the m. And if I have 1 over x to the -m, that's really x to the m. It just moves it upstairs. So it's an elevator, it just moves it upstairs or downstairs. So if I had, for example, 1 over 2 to the -2, that -2 down there would move up to the top to be a +2. So in this case, m is equal to 2. Likewise, if I had 2 to the -2 on top, all that would do is move it down to the bottom. I just wanted to remind you that we already have worked with something in Newton's law of cooling with a negative exponent. It just happened to be that the base was not nice like 2, it was e. So remember that e to the -RT? Well, that's the same thing as 1 over e to the RT with m is equal to RT. So now we know as t gets larger and larger, that denominator is going to get fatter and fatter, and the entire fraction becomes smaller and smaller. Dose response. The way I remember rule number 5 is to remember that x to the 1/2 is really square root of x. We don't really write this, but really square root of x means I'm going to take the second root of x to the 1. So that tells me where to place my fractions when I'm representing a root by a fractional expression. So if I have pth root of a to the q, well, the p is in the same place as the 2, and the 2 belongs in the denominator, so the p goes in the denominator. The q, on the other hand, was the same place as the 1, So I put the q on the numerator. So it tells me using a numerical example where to put everything. So for example, if I had cube root of x squared, the p in this case is 3, the q in this case is 2, and I represent it as x to the 2/3. They're one and the same thing. So that's it for the laws of exponents. Log laws are a little bit more difficult to explain. The most important one is to remember the relationship 10 squared is 100 and log base 10 of 100 is 2. This tells you the connection between the base, which is 10 in this case, between the right-hand side of your exponential equation, 100, and the 2. They're actually all linked together. Logs are just a different way of expressing very large numbers. And in fact, that's why we do log plots. So if the numbers start to get too large, we look at a log plot. So you can check on your calculator that I indeed have everything correct. You have a LOG button. We usually drop the 10 on the LOG just to represent that everybody knows that it's log base 10. And in biology, you use log base 10 more often than you use ln, the natural log. But if you hit the LOG button and look at LOG of 100, you should get 2 as a result. So what do I use this relationship for? Well, it's used to solve things like 2 to the x is equal to 5. How do I use it? Well, here's an example of everything's written down in symbols, log base x, so it not in this case is not log base 10 of a plus c is equal to d. It tells us where it, and you could get a question where any one of these things you're asked to solve for. So you would represent it back in its exponential form. Where does the x go? Well, the same place the 10 went. The 10 was right here. Right here is the 10. That's where the x goes. Where does this d go? Well, the t is at the same place as the 2. This is where the d goes, up at the top. Where does the a plus c go? Well, this a plus c is right over here. It's the 100. So the a plus c goes over here. So I just tell myself over and over, 10 squared is 100, log base 10 is 100, of 100 is 2. You can knock out so many problems that are asked in standard textbooks by using that numerical relationship. Number 2, log of a times b is log of a plus log of b. It's usually used to split off numbers so you can isolate the x. So here's an example. I'm trying to solve log of 2x is equal to 5. And I get log of 2 plus log of x is equal to 5, so I can subtract the log of 2 from both sides, which is approximately 4.7. And now to get rid of that log, to undo the log, well, to undo the log, I have to take the inverse of logging, which is exponentiating. And since it's log base 10, I need to exponentiate by 10, and I get that 10 log x is 10 raised to the 4.7, which I don't really care what that number ends up happening. The whole idea is that I'm trying to extract out x. So I'm using the log laws here to extract out x. I'm not going to go over an example for log of a minus b, a divided by b. That's equal to log of a minus log of b. This one, at number 4, I see more often than properties 2 or 3. And that's when I have an exponent on the a, that the exponent comes out in front. So that then if I have 10 to the x is 100, we actually know the x is 2. What that tells me is if I log both sides, then in this case r is x and a is 10, and I can apply this law to bring the x to the front, and then divide both sides by log 10, and I get, on a calculator, you can usually punch this out. It turns out that log of base 10 of, is 1, and log of 100 is 2, so you get 2. This idea that logs and exponentials are inverses of each other, or back calculations of each other, is what's important. You need to be able to transfer back and forth. The exponential, the natural log, and the e, which is 2.717 dot dot dot, some transcendental number, which I explained why it's interesting to us as mathematicians, are not used as frequently in biology. But we do see it used. In fact, we just saw it used for Newton's law of cooling. So here, the natural log is the inverse of the e, so they undo each other, and vice versa. If I'm taking e to the natural log x, we get x. So they're back calculations one way or the other to transfer back and forth. If I'm using log base 10, instead of having e's there, I would have 10's there. Log of 10 to the x is x, and 10 log of x is x. If I had log base 2 for whatever reason, then it would be log base 2 of 2 to the x is x, and 2 log of 2 base 2 of x is equal to x. How do we use this? Well, I did that problem earlier. I already know that the answer is 2. But again, here I'm going to use the fact that log base 10 of 10 is really just 1, that they inverses of each other. And I just get automatically that x is log of 100, which is 2. And that's it. Those are all your laws. And if you have any questions, just text me or send me an email.